Almost every crop grown in California, and for that matter throughout the western United States, is irrigated. Irrigated agriculture is one of the most efficient forms of crop production on a per unit area basis because growers can control when crops receive the water, the lifeblood of plant growth. Irrigated land roughly produces 2 to 2.5 times the yield and nearly 3 times the crop value per acre compared to rain-fed agriculture. To put irrigation's global importance into perspective, without irrigation technology, the world would need to bring a new rain-fed area roughly the size of Argentina into production to match the output currently produced on irrigated land. But while irrigation brings tremendous benefits, it also comes with important caveats. If there isn't enough drainage throughout the soil profile, salts carried in the irrigation water can accumulate over time, creating potential salinity issues. So what defines salinity? As discussed in episode 3, water salinity is measured by electrical conductivity, or EC, and the same principle applies to soil. Water salinity is expressed as ECW, while soil salinity is expressed as ECE, whereby the E stands for the extract from a saturated paste extract. The saturated paste extract method is the standard procedure for determining soil salinity, and it was derived from the U.S. Salinity Lab decades ago. Both the water and soil salinity are measured and reported in decisiemens per meter or millimoles per centimeter.
There comes a point, however, when sodium becomes the dominant cation of the exchange complex. That's when it's important to distinguish between salinity, which primarily affects the crop by reducing its ability to extract water through osmotic stress, and sodicity, where excess sodium has the potential to degrade soil structure and at times can masquerade as potassium when entering the plant. Soil laboratory measurements such as exchangeable sodium percentage, or ESP, the sodium absorption ratio, or SAR, or soluble sodium can be used to evaluate the potential impact of sodium on soil health. We'll return to sodium in a moment. ECE remains the common language for describing overall salinity. Decades of research at the U.S. Salinity Lab in Riverside, California, established the relationship between ECE and crop yield. There are well-known crop tolerance thresholds developed on more than 90 crops that remain unchanged over the years because they've been proven to be remarkably reliable. These thresholds help growers select crops that are well suited to existing soil conditions or serve as an early warning system when annual soil sampling data shows EC levels increasing over time. To explain these salt tolerance thresholds, which are actually graphs, crops often maintain near full yield potential until a threshold salinity is reached. Beyond that crop's threshold, yield declines with each increment of salinity. Here, strawberry is compared to cotton. Strawberry, being the most salt-sensitive crop grown, has a salinity yield threshold of about 1 decisiemens per meter, versus cotton, which is practically 8 times more salt-tolerant at the threshold of 7.7 decisiemens per meter. Incidentally, the faster that yield declines with these graphs, the more salt-sensitive the crop is. Here's a zoomed-out map of the major crop-growing subregions of California and their various levels of salinity throughout the state. These are 4-year averages across thousands of samples. As you can discern, most of the salinity problems are in the Central Valley on the west side, in the Salinas Valley area, and the southern portions of the state. The Northern Valley gets a tad more precipitation over the winter, has better access to better water quality, and has little to no drainage issues to speak of. All this being said, salinity can ironically protect soil structure by flocculating clay particles due to high calcium and magnesium salts. Yet if those salts are leached past the root zone and proportionally more sodium remains, ECE indeed drops, ESP is maintained, which causes clay dispersion to accelerate due to sodium's large hydrated ionic radius. Although the sodium ion itself is physically smaller, the combination of sodium plus its surrounding water molecules via its hydrated ionic radius is actually larger than that of potassium. When too many sodium ions accumulate, their hydrated ions push clay particles farther apart. The clay swells, so aggregates weaken, and the soil can disperse, reducing water infiltration and aeration. In summary, to improve salinity per se, drainage is essential. Applying enough water to leach salts and perhaps growing more salt-tolerant crops as you're reclaiming the soil. For sodicity, calcium in the form of gypsum or calcium sulfate should be added. Here, it's pure chemistry, knocking sodium off the exchange complex and replacing it with calcium. Salinity management is water management. Every irrigation adds something, except the canals like this probably won't add too much salt because this water is essentially snowmelt. It's when growers start to use wells from questionable aquifers, pulling lower quality water, that the salinization or sodicity problem really emerges. The agricultural retail input industry have numerous products that help mitigate salinity related issues, but leaching the salts with good drainage, using the best water quality possible, and maintaining calcium ions over sodium is the best solution to maintain soil health in an irrigated world.